Welcome to the chemistry walkthrough. In this session, we will learn how to describe a rate of reactions. Well, in the physical world, we have many different kinds of chemical reactions. But how can we describe the rates of these kind of reactions? Well, let's take several examples to illustrate how to describe them. The first one we are quite familiar with is about the reaction between hydrogen and oxygen. Well, we all know that when we want to test for the presence of hydrogen, we'll use a burning splint. During the process, we actually reacting the hydrogen gas with the oxygen gas together with the presence of heat. So in this process, it gives you a slight explosion. That's why you can hear a pop sound. But if the concentration of the hydrogen gas is huge, then the reaction could be explosive. That's why we use hydrogen as a fuel on rockets that launching the space shuttle to the moon. So when we describe this type of reactions, surely we will describe it as a fast reaction, a vigorous reaction, or sometimes we call it a very vigorous reaction. Well, this is quite common to any kind of explosive reactions. But most of the time, the reaction doesn't occur in that fast or in a way that we can still sense the change. So the second example is like putting a magnesium metal into a hydrochloric acid. In this process, you notice hydrochloric acid actually liberates a lot of gas bubbles, and you will not notice the magnesium metal disappeared immediately, but you will notice it dissolved slowly. But still, in a reasonable time, you will notice the metal will disappear. So this type of reaction we describe as moderate. And some of the reactions are really slow. Say, if you put a piece of iron metal on the table with the presence of oxygen and water, it will slowly rust into some brownish yellow colored. So this is surely a kind of slow reaction. Well, in these three examples give us a general idea how to describe certain rates of reaction. But why we want to know the speed or the rates of a reaction? Well, there are some reasons behind though. And the first reason why we want to know is we might want to produce a lot more of the product in a shorter period of time. Say, if I want to produce more water during the explosion, so what should I do so that I can increase the rate, so that I can obtain more water molecules in this case? So sometimes we might want more of the products to be present. Or another reason is we want to increase the productivity. Say, what kind of things what kind of factors is actually affecting the rate of reactions, or at the end affecting the amount of products that produce. So these are some general idea. Well, one example is typically used on illustrating the study of the rate of reaction is a warm pack. Inside a warm pack in the winter time actually it contains a lot of iron. We use a warm pack to produce the iron powder together with some wood powders, some sodium chloride solids, and some activated carbons. Well, when we mix all of them together, we'll notice it will produce certain amount of heat that can warm your hand. But it's not noticeable in terms of the energy when we are touching a simple metal iron article in the winter time. So rusting is actually being speeded up inside a warm pack. This is a kind of speeded up reaction that we might want to understand or study a lot more. So let's really go in depth into the understanding of rate of reaction. So rate of reaction simply tells us how quickly a chemical reaction occurs, and usually it can be defined or measured in terms of the concentration of the products increase over time. Say if I can produce more product in a certain period of time, then surely the rate of the reaction should be increased. Or in another way around, the decrease of the concentration of the reactants per unit time can also be the factor or the standard on measuring the rate of reaction. So we can actually represent or show a key point here, okay, is representing the rate of reaction in terms of a mathematical representation. It's a change of concentration of a reactant of the or product over time. But the thing is, it's rather interesting when we learn how to really calculate a rate of reaction. So let's look at the following equation. In this equation is showing the change of the concentration of product over the change of time. Well, here let me explain a little bit on the change here. Change usually means the final state minus the initial state. Say it's the concentration of the final state minus the concentration at the initial state. Here we have the change of time as well. So means the time at the final state minus the time at the initial state. Well, we can modify this equation a little bit and to make our life a bit easier. So the product concentration at the initial state is always equals to 0, because when we have all the things mixed together, we don't have any product yet. So the concentration of the product equals to 0. And the time at the very beginning, we count it as 0, so it's also 0. So at the end, you can see the equation can be modified and become the concentration of product over the time taken for the reaction. Unlike product, the rate of reaction can also be calculated by the rate of change of the concentration of the reactant, like this. Very similar to the product one, we have the change of the concentration of reactant over the change of time. But this time, we have added a sign, a negative sign. Why we have to add a negative sign? Simply because when we are doing the change of reactant, you will actually notice after some time, when the reaction is finished, say the concentration of the reactant will become 0 at the end. So you have the final state, you have the reactant final state minus the reactant initial state. Well, this one will always be a negative number. That means at the end, when you calculate this part, the change of concentration of reactant over change of time, then this one will become less than 0. But what is the meaning by less than, the rate of reaction is less than 0? Well, it does not make sense though. So we have to add a negative sign showing is a reversed of the overall sign. So here comes a summary on what I've mentioned. The delta P here means the change of concentration of a product in a unit of mole per dm cube. Change of reactants as well is also the change of concentration of the reactant as a mole per dm cube as well. So when we really get into a chemical reaction, let's take one example like this. A will react with decompose and become 2B. That means if we are really writing the rates of this reaction, we can represent the rates of the reaction like this. The change of the reactant, this time A is the reactant, over the change of time, and multiply a negative sign in front of it. Well, that's true. But when you look at it, the mole ratio between A and B here is 1 to 2. That means when you have 1A, you produce 2B at the same time. When you lose 1A, you produce 2B. That means the rate of decreasing A will become producing 2B. So how to calculate the rates of the reaction in terms of the concentration of B then? Then we have to know about the mole ratio. So just as what we have mentioned, okay, the mole ratio is 1 to 2. So at the end, when we know the rate of reaction of A is, say, a value of X, then we have to use the mole ratio to calculate the rates of change of the B. If I have 1 mole of A, then I will produce 2 B. Then that means the rate of reaction calculated by B will be twice as fast as the A. So we have to multiply this number by 1.5. Then you will know what is the rate of reaction of the change of A. So in summary, in this session we know how to describe how a reaction looks like. We can describe as fast, moderate, and slow. And the second one, we know how to determine a rate of reaction simply by doing the change of concentration over change of time. See whether it is a product or a reactant. And lastly, we have mentioned when we calculate the rates of the reaction, we have to be very careful on the mole ratio as well. So this is the end of this part. Thank you for watching.